Hi, this is Physics Lab 4, where we will be observing a spring mass system parallel to an extreme sports video of a swinging rope from an arc. The objectives in this lab are as follows. We will observe the motion of a spring mass system, construct a computational model of the motion, and apply the energy principle to the system. With all this being said, these three steps will allow us to find the similarities in the oscillating spring mass system mirrored in the extreme sports video. Some previous principles we will apply include Newton's second law and the spring force equation, as well as we will incorporate new principles which include the transfer of energy, utilizing equations such as gravitational potential energy, spring potential energy, and kinetic energy as seen here. We extracted data from a tracker video in order to construct our computational model. The video is shown here where the only forces acting on the weight are gravity and a spring force. We track the separate data points in the coordinate system and analyze the motion of both the x and y components. The initial conditions of the tracker video are as follows. We then utilized the spring equation and found the period for the oscillation of the string and tracker to find out the unknown spring constant as seen here, which turned out to equal approximately 6.84 newtons per meter. We are now ready to construct the code for this model. After setting the initial conditions, we put in the crucial components of the fundamental principles. Newton's second law is seen here, showing how the weight will change with velocity and position during each time step. Once again, the only forces acting on the weight are spring force and gravity, as calculated above as well. We now move to the energy principle here, where kinetic energy, gravitational potential energy, spring potential energy are all components confined in this system, and the respective equations are seen here. We will now run the code, focusing on the tracker video motion of the spring system and the computational model we made for it. As you can see, the model is fairly accurate, and the small discrepancy in motion can be accounted for in very slight factors such as drag or imperfections in tracker points. The oscillations of the spring evidently display how each period showcases the continuous interaction of spring force and gravity. We will now observe the individual contributions of different energy. We run the code showing each separate energy as separate graphs. The red line is the change in spring potential energy, the blue line is change in kinetic energy, the green line is change in gravitational potential energy, and the yellow line is the total energy. Notice how the total energy is constantly equal to 0. All the energy follow the oscillations of the spring. Kinetic energy will equal 0 when it momentarily rests to change direction, and the potential energy of the spring and gravitational are opposite. So what does it mean? Since there are no external forces acting on the system besides gravity and spring, no other work is done besides these elements. No external work on the system means the energy is equal to 0, following the energy principle as seen here. The different oscillation periods for x and y components are seen due to different values in the equation for respective periods. The difference in periods between the x and y are approximately equal to 0.2 seconds, also signifying the elliptical motion of the weight on the spring for the x-axis. When applying this to the original problem of the extreme sports video, we can see that the oscillation is heavily relying more on a pendulum motion with emphasis on the x component with a longer period. And that concludes this lab.